So here I was introducing you the unit vectors I, j and k in the three directions x, y and z respectively, which are mutually perpendicular, are orthogonal to each other. And the one thing which I introduced was that the values of all these vectors is equal to 1. The direction vectors, the magnitude appears to be 1 of each of them. And as an application to describe a vector, position vector r, I said I have the components x, y and z corresponding to this vector r. They could be negative, they could be 0, they could be positive, they can have any set of values, and then we are able to express it as the component vectors multiplied by their respective unit vectors to establish it. And now I will rewrite that and tell you something more so that we understand much better. So in a system of three-dimensional situation, I redraw the axes x, y and z, z, x and y. These axes where these angles that they make with each other, they are 90 degrees each. But if this happens only when we go in the right direction of rotation, this 90 degrees, the axis x makes an angle of minus 90 degrees here with the axis y. The axis z makes an angle of minus 90 degrees with the y-axis, and the z-axis makes an angle of 90 degrees minus with the x-axis. So here I take this position vector which I call r, and here I have the component vector rx. This is the component vector with a magnitude equal to rx, a component vector which I can write ry in the y direction, and a magnitude equal to ry, and then I can write a component vector rz in the z direction, and of course the magnitude of this becomes equal to rz. So I wrote, for example, that my vector r is equal to rx, the x component, I cap plus ry, j cap plus rz, k cap, where these are the variables. I'll show to you that these things rx, ry, rz may have any negative or positive values and also a zero value. They are variables. R is a variable, but the I, j and k, they are invariants. So I just give it a symbol like this, that this is constant, which we are not able to change, which we will not change because they do not change their directions. Once the x, y and z axes are specified, then we have the specification I cap, we have the specification j cap, and k cap. So the values Rx, Ry and Rz, they can change. I, j and k remain the same. Now I'll show you that if we had only two directions, x and y, the two axes, then I can redraw the y-axis and the x-axis like this, and I have the component here which is r x in the x direction, this is the component ry in the y direction, and then if we try to see as to what is the resultant, we can use the situation that the vector rx here, the vector rx here, and the vector ry here, the vector ry here, they add up. What I obtain? I can shift the vector ry to this position to obtain, I will just draw a line parallel to it, and this vector becomes nothing but a shifted vector ry. So now you can see by the law of either you say that the parallelogram of vectors, if you allow me to complete this parallelogram, then I have just this one line from here to here. This is of course a rectangle, but this vector again is equal to the vector rx. So I have Rx represented either by this line or by this line, which are parallel to each other, and Ry represented by this line as also this line, which are parallel to each other. From parallelogram law of vector addition, we find that the resultant vector which results here for this turns out to be equal to Rx plus vector Rx plus vector Ry, and the same is true for the tail to head system, that from this tail to this head I am drawing this line, and therefore I get the two vectors Rx and Ry over here. And of course for this particular thing I can have this angle theta, which is again a positive angle as it appears over here. Could be negative if the line would have been drawn like this. So then this is Ry, Rx, okay. So Rx plus Ry gives a vector like this, and from the, either you use the Pythagoras theorem where I have a right angle triangle here, and this is the base, this is the perpendicular, and this is the hypotenuse, then we find that the magnitude of Rx plus Ry, Rx plus Ry, this magnitude, if I square it, of course I know that the value of this is Rx, so if I square it, then this will turn out to be equal to the base, which is Rx square plus the Ry square, which is the magnitude along the y-axis. So therefore I can say that the magnitude of the vector that we have obtained by addition Rx plus Ry, this magnitude, we can give it a name, but I will not. I'll leave it to you to give it a name and obtain values. So this will be equal to under root of Rx square plus Ry square. Okay? And also that from here, because this is Rx and this is Ry, then you know from the trigonometrical definition that tan of theta, tan of the angle theta is equal to Ry, the magnitude, divided by Rx, the magnitude. So this is how we are going to specify the theta, and we write theta is equal to, therefore my theta, the angle, is equal to tan inverse. Tan inverse. This is how we write tan inverse Ry, the operation of tan, and the operation, the reverse operation, that I'll get as Rx. So the angle theta has been described. The angle theta has been obtained as the tan inverse of Ry upon Rx, which is also sometimes written as arctan of Ry, whatever, on Rx. So if there were a sign relation, this will turn out, theta will turn out to be the sine inverse of that quantity, that's a number, and that we'll write arc sine. Cosine having a certain value over here, then the theta will become equal to cos inverse of that value or arc cos of that value. So anyway, it doesn't matter. So I have found the magnitude over here, to be equal to under root Rx square plus Ry square. Now if suppose this is in the three-dimensional space. So in the three-dimensional space, if suppose I obtain it like this, or maybe if I open this line, so I have obtained, this is my x-axis and this is my y-axis, and I have got a line, the resultant of these two, as a line like this. So this value is Rx, this value is Ry, and this value is under root of Rx square plus Ry square. So this line, now look here, please look here, that the third direction is my z direction.
That is not visible. इसको थोड़ा slant कीजिए ऐसा.
Okay. So the third direction is like this, and you can see that the third direction also makes an angle of 90 degrees with this resultant. So in the next stage, what we say is that for the total thing, we can write that the value of r, which is like this will be equal to the magnitude that we obtained over here, which is Rx plus square plus Ry square under root. This is, I can write it as, using the same kind of the trigonometrical relationship, I can write it as Rx square plus Ry square under root under root whole square plus RZ square. And we can also find the angle between this RZ and this direction, etc., etc. So this will turn out to be equal to Rx square, the magnitude square, plus Ry square plus Rz square. Okay. So the magnitude of the resultant vector in terms of the component vectors Rx, Ry, Rz along the directions x, y and z, this turns out to be equal to, this is not the magnitude, this is the square of the magnitude, which should be like this. So allow me to write this equation again, and then I will utter a few more words about it. Okay, this I will remain. Okay, I will rather write here. So I have the magnitude of the three component vectors are given to us in these directions. Then I write that R square is equal to Rx square plus Ry square plus Rz square, the component vectors. And therefore my R will be equal to Rx square plus Ry square plus Rz square under root, or we can just put to the power half. So this is how we are able to express a vector which has three components along the x, y and z axis in terms of the I, j, k vectors multiplied by these values, and then we obtain things like this. I will return it to you how we obtain this relationship, this kind of relationship, after we consider and hear itself. It may take some time as to what is the multiplication of vectors. In the multiplication of vectors, the first thing is there are three types of things. One where I have a vector, A, and this is multiplied by a scalar quantity. A scalar which has, so what we get is a new vector, and this vector ought to be parallel to the first vector, and let us say this vector. So I get a scalar into vector product where we obtain a new vector. Say I call it a vector A star. I'll give you some examples, and a couple of examples will do where you understand what it means. For example, I have a velocity vector, and we multiply it. So this multiplication sign that we are going to use, I am going to use this star. This is multiplied by a scalar m, which is mass. And so m into v gives us a vector, as per definition also, a vector p, which we call the momentum vector. The momentum vector is parallel to the velocity vector and in the same direction that the velocity vector is there, and from this equation I can also write that 1 upon m I don't know how to make you visualize what is 1 upon m multiplied by the vector p will give us the vector v. So these are the vectors which are multiplied by this quantity. For example, I can also show to you that if I had a vector acceleration vector, which I have defined for you before, and I multiply it with the mass vector, then I obtain what is known as the force vector measured in newtons. Or if I multiply the force vector by this, I'll get an acceleration vector, and you can see that the new vectors which I obtain on the right hand side, they are in the same direction as the old vectors, P with V, V with P, F with A with F, etc., etc. So this is known as the multiplication of vector by a scalar. Also, a vector can be multiplied in similar manner by a number, and that number could be positive, could be negative, would often be equal to 0. Okay, so this is the thing. Now, the second thing that I have, and I must define about the vector multiplications. I will have occasion to write things again, but right now I am going for the scalar R dot dot in bracket, it is like this, dot product. In the dot product, at least we have got two vectors where we multiply one vector with the other vector and try to find out as to what are the relations. The way we write it, it's interesting that I have a vector A and another vector B, and the product is a scalar. The product is a scalar. We don't get any vector on the right hand side. The product of A dot B is a scalar. And we say, allow me that A dot B is equal to magnitude A to magnitude B into cosine of theta. AB cos of theta. Now I'll just to tell you a bit more, I will use again what I left before, just two lines. I'm drawing a vector A, and with a positive angle I draw the other vector, vector B. Now one first question is that how about the vectors A and B and what families they belong to? So my answer to you is A and B can be of the same family and they can be of different families. The angle between the two of them is theta here, and if I drop a perpendicular from the head of the vector B, then I get this as the vector A and this magnitude A, magnitude B, and then I have this as equal to B cos of theta. So you can see these are two set of things, A and B cos of theta, and if I put the b cos of theta here on the same axis or draw another one. You can always draw as many things as possible. I have my constraints, you don't have. You are rich people, you have the paper, you can always draw, you can always cut it, whatever. And then I get, allow me, I'll get a something like this. I'll get a rectangle, and I can find just what is the area which is covered by the rectangle, etc. This is now, in this case, I will shift it, and just to make you understand, d cos of theta, and this is a, and therefore these two quantities are multiplied with each other. So the area now becomes in the units of the unit of a multiplied by unit of b. Of course, the cos theta has got no this thing. So what I will get? I'll get something which I can write ab cos theta. Okay, so a and b, these two vectors of the same kind or of different kinds, and then I get ab cos of theta. So with this definition that I have got over here, the value that I have got over here, as there is a very interesting feature. Now I ask you to tell me what is b dot a. B dot a. So b dot a will become equal to, by the same way, in the same string, for a I'll write b, for b I'll write a, but now the angle that was there between the two of them, the angle has reversed. This angle has become cos of minus theta. Cos of minus theta. And as I told you, that this is equal to ba cos theta itself, because cos of minus theta is equal to cos of theta. Cos of theta. Well, I will let you know now again as to why cos of minus theta is equal to cos of theta, and why sine of minus theta is equal to minus sine of theta, with a simple trigonometrical thing. I'll draw the reference circle. I'll draw the reference circle. I'll draw the axes x and y, and now I'll just show to you that this is y prime, or minus y axis, x prime, which is in the negative direction, okay, what we also called a dash. And now with reference to the x axis, I have a drawn on this circle the angle theta. And you can see, and then allow me to drop the perpendicular, which I will extend just like that and talk to you later about it, that if these two are equal, and then I have, this will suffice to explain to you that this angle is plus theta and this angle is clockwise, and therefore this is minus theta. Okay. In the first instance, I am going to use the red pen, and I will use the hypotenuse, the perpendicular, and the base for the positive angle. And using the other pen, I'll say that in this case, if it is negative, this is the perpendicular, this is the base, and this is the hypotenuse. Now one thing I'll just tell you, that hypotenuse is always positive, okay, but this direction is negative and this direction is negative, this direction is positive and this direction is positive. So if I say that for the case of cos theta, I'll write this as equal to b upon b, b upon h, b upon h divided by, in the case of minus cos theta, b by h. In the case of cos of minus theta, this turns out to be equal to b upon h, b divided by h. So you can see b in both cases is common, is from left to right in the positive direction of x, and of course h does not have any direction. This is equal to this is equal to itself, of course, is so obvious. Okay, so therefore the cos of minus theta is equal to b upon h, which is equal to, I can write b upon h, which is equal to cos of theta. And just giving you a hint to show that sine of minus theta is equal to minus sine theta. Here please look that this perpendicular goes in the negative direction, whereas this perpendicular is in the positive direction. So this is p upon h as sine of theta, and this is in the negative direction. So p becomes negative, this green p becomes negative, h remains without that. So we can directly write the result I have already done, that sine of minus theta is equal to minus times sine of theta. So you should be able to tell these relations just like you start buttoning your shirt like this. So you don't need to see as to where is the button and where is the you have to put the button, the hook is there, etc., etc. So let me go back to here. With that explanation, I go back here. So what I obtained is that A dot B is equal to B dot A. That means my vector A can commute from this position, the first position, to the second position, and this from the second position it may come back to the first position, and therefore what we'll say it? This is, the process is commutative. What it is? It is commutative. So commutative I introduced to you before. Commutative. I will have an occasion just to tell you about this, not more, about the scalar dot product, because the other product is very interesting, still I'll have to do it because it will be very bulky otherwise. Now one thing, suppose B and A, they belong to the same family, and I want you to know as to what is the vector A dot itself, A dot A. So what will happen from this definition? A, B cos of theta. This will become equal to magnitude A into magnitude A into cos of 0. Degree or radian or whatever you want to say. And cos of 0 is equal to 1. And therefore this turns out to be equal to A square. A square. So I have a relation now to ponder that my A square is equal to A dot A, or my A is related to this dot product of two like vectors of the same magnitude, the same family as vector A dot vector A under root. Okay, so this is one thing. The second thing is that just to find out the value of this cos theta over here, I can, and I will leave you at that, I can and write from this and the relation that cos of theta, the angle between the two vectors A and B, this is equal to, if I am given the dot product A dot B, as also we can find out the values of A and B, then I can write just that this is equal to A dot B into AB, in A multiplied by B. So finally I leave you here that the theta will become equal to, I can calculate, is equal to cos inverse of A dot B divided by AB. I'll not move on to the beautiful other product, the third product for a vector. Okay, so theta will turn out to be cos inverse A dot B divided by AB, or cos of this quantity. So we can calculate, of course, the value of A, value of B by the formula that we had. Okay, for example, if I write, okay, I'll take a bit of time more. If I write that there is a vector A which has a component in the x direction, AX, I cap plus AY, the component along y direction, J cap plus AZ, K cap. So what is the value of A? I know the components and I want to calculate the value of A, and I am going to write the result directly like I was taught, and I made a practice. You practice and you can also write it like that. This will be equal to AX square plus AY square plus AZ square under root. Similarly, you can find out the value of B here, and of course, if the two vectors are given to you, you can write A dot B. Okay, something I'll tell you numerically, and thereafter I go to tell you what is I cap dot I cap, what is I cap dot J cap, what is I cap dot K cap, or J dot I, and here K dot I cap. Similarly, any similar expression for J cap dot J cap, K cap dot K cap, and I invite you to go through whatever sources you have, and then we'll talk about this interesting thing wherein we can obtain, how to obtain if the values are there, and how we obtain the dot products of these quantities. It may take some time, 20 odd minutes, but I have plenty of time, you have plenty of time. Follow me and enjoy. Thank you very much.